So this lesson today will be on point charges in magnetic fields, essentially the path followed by moving charges in uniform magnetic fields. So going back to our previous lessons, what is a uniform? So what is a uniform magnetic field? Well, a uniform magnetic field is one of constant strength and direction. And we can use the right-hand slab rule, which we've gone through previously, and see that the force on a charge is at a right angle to the velocity of that charge. This means the force cannot change the velocity of the charge, however, it can change its direction. Right, so here we have an electron beam, a series of electrons going into a magnetic field which is going into the page. That's what the crosses mean, it's moving away from us. And you can see that the force exerted on the electron beam is going down. Now, how do we know this? It's because of the right-hand slab rule. Now remember, of course, in the right-hand slab rule that we're dealing with conventional current, so it's going from positive to negative. So an electron being negatively charged particle is negative. That means it's going from negative to positive, so we have to reverse it. So the direction of the conventional current in this particular case is going to be the thumb, and it's going in that direction. Okay. Now we know that the magnetic field is the fingers. It's going into the page, so it means that the force exerted on the electron is going down. Now, it's very important that you use conventional current in dealing with the right-hand slab rule, not thinking that the direction of the electron beam is the direction of the current. It's in fact the opposite because we use conventional current in the rules. Okay, so you can also see from the right-hand slab rule that the velocity of the electron is always at right angles to the force being exerted on the electron. And the magnetic force is always towards the center of the magnetic field. This means the electron moves in a circular path, and we observe this experimentally, as you can see from the following image in a cyclotron. Okay, so you can see that the electrons are moving around in a circle in a uniform magnetic field. Okay, so here's an example from an exam paper on how we would apply the learning today in an exam situation, in an exam question. Now, you must also remember that you will have to apply other areas, other sections of work to electromagnetism questions. For example, in the question here, we're going to be looking at circular motion and Newton's laws in mechanics. But just to illustrate, here's an example. So, in a particle accelerator, a proton travels at about 3 times 10 to the 7 meters per second in a magnetic field strength of 0.6 Tesla. And the charge on the proton is 1.6 times 10 to the negative 19 coulombs. And I've illustrated that in the diagram. So what I want you to do is to first find the size and direction of the force of the proton, acting on the proton, and then find the radius of the circular path followed by the proton, given that the mass of the proton is 1.6 times 10 to the negative 27 kilograms. So the first thing I suggest you do when you're asking this question is underline all the variables and see if you can find equations which fit the question, and you'll be given a list of equations in the exam. Okay, so pause the video now, and in the next slide we're going to go through the answers. Okay, so hopefully you've got the answers, and if not, you can look at this next slide and see where you've made mistakes and where you can improve. Right, so the first thing we were asked to do in part A was to find the force on the proton. Now, looking at the equations that we had a charge. Okay, so we know what the charge is. We know what the velocity is, it's given. Okay, and we're also given the size of the magnetic field. Okay, so we have Q, V, and B. So do we know any equations which can fit within that? Of course we do. We know that the force equals Q, V, B. Okay, so all we have to do then is just plug in the numbers. So we know what Q is. Q is given as 1.6 times 10 to the negative 19 coulombs. The velocity or the speed of the proton was given at 3 times 10 to the 7, okay, meters per second. And we were also told that the field strength was 0.6 Tesla, so there we go, Tesla. So if we just multiply those numbers together, we get an answer of 2.9 times 10 to the negative 12, and of course the units being force are newtons. Okay. We're also asked to determine what the direction is, so we use the right hand slap rule, and from that we can work out that the direction of the force will be to the right. Okay, so that's the answer for the first one, so it's to the right. Okay, pretty good. Okay, so next question says that we're going to find the radius of the circular path followed by the proton, knowing that the mass of the proton is 1.6 times 10 to the negative 27 kilograms. So what equations do we need to know? Well, we know what the force is. We're just going to do it in part A. So we know what the force is. We have a mass, and we have to find the acceleration. Okay, so we don't know what that is. However, we know that the acceleration in circular motion is v squared, which we know, over the radius. Okay? So as we know that the force equals m v squared over r, because we can plug that into Newton's first law of force, is ma. Okay, and plug that in, substitute for a. We can then rearrange that to get the radius equals mv squared over the force, which will equal, if we plug the numbers in, 1.7 times 10 to the negative 27 kilograms multiplied by the velocity squared, 3 times 10 to the 7 all squared, and this is all divided by the force, which we worked out in the first question, part A. Okay, so if you do the calculations, you get a radius of 0.53 meters, and that is the answer. So applications. Well, I thought for applications I'd bring back nuclear physics to help remind you of that topic. So in nuclear physics, we learned that in 1898, Bernard Rutherford, New Zealand research scientist in Manchester University, passed radiation formed by radioactive polonium through a magnetic field, which you should all remember. And we saw that some radiation was deflected up, some was deflected down, and some were not even deflected, just went straight through. This is kind of what he saw in terms of a magnetic field, or passing these radioactive particles through a magnetic field coming away into you, towards you, or that's what the dots. And what he saw was through the right hand slab, where you can work out what the charges are. He deduced that there were three types of radiation: the positively charged alpha particles, which we see here, the negatively charged beta particles, which we see here, and the uncharged gamma ray source which weren't deflected at all. Okay, because the magnetic field is out of the page, okay, so looking at the first example, alpha, so it's going using the right hand slap rule, direction of the thumb is to our right, the field is going out of the page, the force is of course coming down, from which we observed. Notice too that depending on the velocity of the beta particle, the radius of the circle will be different, larger for high energy particles and smaller for low energy particles, and we related that back to our last example in terms of the equations of circular motion. So that's pretty much it for the examples of a path followed by a moving charge and a uniform magnetic field. In short, the answer to that is a circle, and the reason why is due to the fact that the force, the magnetic force exerted on a charged particle, is perpendicular to the velocity of